考卷还有问题的同学，那就是今天5点半开始的研习课，助教会告诉你们标准答案。然后如果你有问题的话呢，请你在研习课跟助教讨论。然后呢，讨论出一个结论来之后，请助教当场更改你的成绩。那如果还有得不到共识的地方，就可以在星期五的时候上课和星期五下课的时候来找我。So students can pick their exam sheets up, and if you have questions, then you can go to the recitation session today from 5:30, and you can have a discussion with the TAs face to face. And if you can have a conclusion, then just correct your credits right on the spot. And if you are not able to get into a conclusion, then you can come to me on Friday, just after the lecture, please. So then we can discuss it. So when I look at the credits I have, I really don't have that. I really don't think that is really a big problem. Now I have a big problem because the credits are too high, and I will be in a big dilemma when I'm processing your final record. 就是我看了一下你们的分数，这次有问题的同学应该是不多啦，有问题的人就是我了。请问我怎么计算你的成绩？我又要被教务处警告了。加分题给太多了。好啦，没关系，大家成绩很好，这样很好。OK， 那我就要直接开始上课喽。我们今天要上很猛的。So now I'm just starting the lecture, and today we are going to do a very hard job. Today is a hard job, but it's my favorite part in physics, and every time when I'm giving this lecture, I always feel very, very happy and very excited. This is a session that I really like very much, and every time when I come back to this, I always get new inspirations, and I always get myself into a historical vibe that that was a very interesting time in physics, and I will explain why is it like that. I would say it's just like a detective novel, but written in a very bad way. But because it's written in a very bad way, so when you're looking at it and you feel this is so realistic but so spectacular. So I like it really, really much. So we start from black body radiation, and I just introduced the physical origin of black body radiation. That is because the charge carriers in material, and they are vibrating when the temperature is getting hotter. And you can remind yourself what we learned in statistical physics and thermophysics in last semester. Sorry, let me check if the broadcasting is working or not. Yeah, it should be working. Okay, let's go on. And I just gave an introduction to you. Sometimes we use the unit which is called color temperature to describe the colors of the light. So this is what you can pay attention to when you're buying your light bulbs. And this is the spectrum of black body radiation. And when you look at the spectrum, you can see that when the temperature is getting higher, the intensity of the light is getting bigger. And the distribution have a peak. And the peak is in most of the parts with the largest intensity, they are in the range of visible light. So this is the reason why people start to pay attention to black body radiation, and the theorists, they are very interested in it, and they would like to derive it theoretically. They would like to start from a theory, and they would like to do the derivation and see if they can get a distribution like that or not. But the question is, now this is the most important part. They just find that the theory doesn't work at all. And here is, I just start from the experiment. So this is how we do the experiment when people are working with black body radiation. They have a tube like this, and they just paint it and make it all black inside. And in order to increase the opportunity of reflection to every kind of directions, they don't want a reflection like it's single direction. They would like to do it in multi-directions, and therefore they just make a lot of bumps, like up and downs, just inside in the inside surface of the black tube, and they just heat it up, and let the black body radiation happen. And the photon inside, they will go back and forth, and until they somehow by chance get into the path of a little hole, and the little hole just come out of the black body tube by the little hole. So that is how they do the black body radiation, and they can really calculate the vibrating modes of the light because they know the geometry of the tube. And we can just calculate it. You can think about standing waves, and the way that the radiation is vibrating in the tube is the three-dimensional standing wave in spherical confinements. So I'm not going to give you the graphical explanation now. You can think about it by yourself. You can imagine it by yourself in your head. So if you count the numbers of types of standing waves, and you just count 1, 2, 3, 4, and it really depends on the wavelength of the light, isn't it? So if the wavelength of the light is very long, and you don't have that much possibilities, but if you have a very short wavelength, and there are so many combinations of different modes of standing waves, and then you can have many, many different possibilities. And then if you count it that way, you can get the spectrum of black body radiation. This one. This is just the spectrum. Hello, your roommate is calling you, and yeah. Yeah. I think we should put the exam sheets at the back.
Yes.
Yeah. So please, I just get it back in. Okay, so let's. The theoreticists, they just start to think about it this way. They do some derivation. This is the installation for the experiment, and this is the tube for the black body radiation. And here is a lot of light path. This is the optical path because you have a lot of optics to analyze the colors of the light, the intensity of the light, and you try to analyze it and try to draw the spectrum. And this is how they analyze the colors of the light. They have a prism, and here are some other installations that can make your dispersion wider, and then you get higher resolution for your spectrum. Then, if you're interested, then you can read it. And this is a paper about the history for the discovery of black body radiation, and if you are interested, you can just get into the paper and read it. Okay, but then here comes the big problem. So when we do the experiment, and we start from this spectrum. So this spectrum is the intensity versus wavelength, and we do the experiment, and then we are very clear about the experimental outcome. But if you just follow the logic that I just described, and if you derive it theoretically, and the theoreticists discover that no, they are not able to reproduce the spectrum like that, and this is what they get due to the theory. And this doesn't make sense at all, because when your wavelength is getting shorter, and the theory just said that the intensity of the light should be getting bigger and bigger and bigger and to infinity. And how could it be possible? And this is the experimental result that when we have a shorter wavelength and the intensity should be approached to zero. And somehow we have a peak, and the position of the peak is very important for this spectrum because it depends on the temperature, but somehow we are not able to reproduce it with the classical theory. So what's going wrong? And if we switch the spectrum to intensity versus frequency, wavelength and frequency is just you can just convert it, isn't it? And if we use the classical theory, and this is what we get: frequency, higher frequency, shorter wavelength, and intensity gets to infinity, and this is strange. And if we just follow the experiment, and we always get a spectrum like this. And now here's a big problem. So what's going on, or what's wrong with our expectation of the behavior of the photon? Okay, and here is the model of the black body radiation when the theorists are deriving that distribution. So we can imagine that our black body is just like a box, and the box is placed on fire. So the fire heats the box up, and our photons, the radiation, and the radiation is just the vibrating energy that does the up and downs of all the energies. And if the wavelength of our radiation, and somehow it matches the condition for a sending wave, and this is the reason why that when we are measuring the wavelength of black body radiation, and then you can separate it and then you can get different colors. And here is a box, and box is three-dimensional, and this is how the sending wave will look like. So this is a possibility, another possibility, the third possibility, and the fourth possibilities. And you can start to try to do a lot of combinations of different possibilities in 3 dimensions, and then you can just imagine it by yourself. And now let's just think about what are the parameters for the intensity of radiation. Intensity of the radiation is the strength of the radiation. So what are the conditions that can make it stronger or make it weaker? And the theorists, they just find 3 crucial parameters. The first of them is the number of vibrating modes. The mode is, you can imagine it is the shape of the sending wave. It's the number of the modes. The second parameter is the energy per mode. So every vibration, it contains energies, and energies is switching back and forth between potential energies and kinetic energies, and that is how we model oscillations, isn't it? And so every kind of mode of oscillations, they have a particular energy, and so how much energy is contained in that mode. Okay, and the third one is the probability per mode. So the probability of a mode to happen. So some of the vibration is very easy to happen, and some of the vibration is very difficult to happen. And so that is the factor related to the probability per mode, and the number of the modes, energy per mode, and probability per mode is a function of the frequency. So this is the very important part. This is how we do the model. The 3 parameters. And honestly, I think it takes a very long time for the statistical physicists to find out these 3 parameters. Every time when you're building a model, the most difficult part is to find the parameters that make sense. And if you work with the model for a really long time, and then you can find a lot of parameters, and some of them are very crucial, some of them are minor. Okay, and here are the 3 crucial parameters. And then, okay, and now I am running an exercise in the lecture, and when we are deriving the spectrum of black body radiation, I also would like to show you a very important method to estimate something. And we don't teach it that much in Taiwan, in Taiwanese education. Somehow we don't have that kind of techniques to think. But this is what I learned when I was a student in Germany, and in the German educations, and they introduced this kind of method a lot. So when we work on black body radiation today, and I would like to also at the same time and teach you how to think this way. 那今天就是在带大家推导那个黑体辐射的 spectrum 的时候，我顺便想要教大家一个很有用的应该算是一个推导的技巧。然后我不晓得为什么在台湾的教育里面好像从来没有人教过我们做这件事情。然后这个是我在德国的时候学到的。然后德国人在教物理的时候，基本上这个方法他会用在所有的事情上面。然后呢，我觉得它的好处就是你会对于参数跟结果，你会有一个非常清楚的概念。所以我们今天呢，就是顺便一起来教大家这件事要怎么做。好，然后通常这个也是我们在普物课本或者是你在网络上找，你都不会找到的。大家讲黑体辐射的时候，只会快速带过，因为其实黑体辐射的本体是很难的东西，所以大家都可以跳过。但是我知道荣誉班的同学是不会满足的，一定会入围，所以我决定，好，那我们就来玩真的。好，那我现在把纸下去。And usually black body radiation is too vaguely summarized in textbooks and in all kinds of information on the internet, because people doesn't. If you really read the paper written by Planck, it's also very hard to understand why he derived everything that way and how he get into conclusion. So that's the reason why when all the teachers try to explain it, they get stuck. And they just skip the most important part and directly get into the conclusion. And I'm sure students are not getting satisfied, and I wasn't satisfied too. So, and this is what I learned when I was a PhD student in Germany. We started derivations from scratch, and I was like, okay, so that is what is really happening. And so now I'm telling you the story. Of course, it's not the original story. It's digested by my German teachers. OK， 所以今天呢，我就跟大家说，我自己在德国当研究生的时候学近代物理，然后这是我在德国学到的版本。那当然，它也不是原版的，这个是我的老师他消化过之后教给我们的东西哦。那我自己也有在消化过一次。OK， so when you have the paper, and please prepare these 6 coordinates. So 3 of them is for the classical model. And 3 of them is for the quantum mechanical model. And just remind you, Planck doesn't believe in quantum mechanics at all. Although he derived it, but he doesn't believe it at all. So I'm sure if just look at the quantum mechanics, he is getting very, very angry at it. But anyway, he's not here. 就是普朗克本人哦，他自己虽然很成功的解开了这个问题，可是他不相信这世界上有量子力学这种东西。所以如果他看到我在他的东西上面写个 quantum mechanics， 他一定会非常生气。但是不管他，反正他不会过来。好。And the three coordinates. The first one is the number of modes versus the frequency of light. The second one is the energy per mode. The third one is probability per mode. And when you're ready with the coordinates, and just on the upper right corner, just write your name and your student ID.
然后你把六个x y 轴，就是6个坐标系统都准备好以后，然后记得写上你的名字跟序号。右上角挑一个角落写你的名字跟序号。然后因为这个突然之间资讯有点多，我解释一下。第一个图呢，我们要画number of mode， 就是你在某一个，如果它光有一个特定的频率，它可以在你的黑体的那个腔里面可以产生多少个振动模式，所以这是第一个图 number of mode。第二个图是每一个振动模式呢，它需要多少能量，就是 energy per mode as a function of frequency。然后第三个是呢，每一个振动模式它到底有多少几率会发生，所以是 probability of mode。然后3个都是频率的函数。OK 了吗？画完了吗？还需要时间的，举手，然后看一下。If you still need a little bit of more time, please just press your hand. Okay, so 1 minute. 普朗克在德国是一个非常受欢迎的物理学家，就是人们喜欢他，应该比喜欢爱因斯坦多。So Planck is a very favorable and admirable physicist in Germany. It feels like people like Planck more than Einstein because Planck is very gentle. Planck is very humble and he is very wise in a way, and that really matches the imagination of a good man of the German hearts. So they like Planck really much. And every country have a research institute, the central one, and then all the scientists are there working for the country, just like Academia Sinica in Taiwan, 就像台湾的中央研究院。And the Academia Sinica of Germany is called the Max Planck Institute. 就是德国的中央研究院呢，它不叫中央研究院，它叫 Max Planck 研究所。你就知道，大家在德国，大家是非常推崇普朗克，因为普朗克是一个很谦虚的人，就是他很谦虚，然后他人很好嘛，普朗克就是人很好，然后而且他是格言之王，就是他常常会讲出一些让人觉得非常有智慧的话。基本上德国人都非常喜欢他。我就是因为他这么的谦虚，所以他不是很喜欢就是弄一些很花俏的想法。 就算他自己已经发现这种爆炸性的事情，他还是觉得他应该是哪里搞错，所以他就没有认为说我这个东西很厉害或者怎么样。好，看起来应该是 OK 的。So seems like everybody is ready. So we go on with the next step. Okay. So this is the distribution of number of modes as a function of the frequency of light. And basically this is what we get with the classical theory. And I just directly give you the results. If you are very interested in the derivations, and then you can just go to this web page. You can download the slide from our New E3 website, and here's a very good web page and showing you how to derive it. We don't have time to derive it right here, right now. Usually we do it in the lecture of solid-state physics when you are in the 4th year of university, but it's not very difficult. The derivation is not very difficult. It's just some logical thinking. But if I'm interested, then you can look at it. I can just directly tell you the answer. So if the frequency of the light is higher, which means that the wavelength of the light is shorter, and we have more possibilities of vibrating modes in it. So if your box is that big, and if the wavelength is just like that, and then you have many different kinds of combinations to put the wavelength inside. And then the tendency is the square of the frequency. The 8 pi is from the geometry, and c is the speed of light. So it should be a curve going up like this, and the trend is the square of your frequency. And in classical theory and in quantum mechanical theory, we get exactly the same thing. Up to here, there is no difference between the two theory systems. Somebody is still writing. And then we are working with the next one. Sorry, here's the explanations. I forgot that I have the explanation. So this is what I just said. So this is with longer wavelength, lower frequency, and this is with a shorter wavelength and higher frequency. And you can see that this is the reason why when your wave is going to different directions, and they have many conditions that matches the requirement for a sine wave. And this is the reason why you have more modes. You have more modes of vibrations. Okay, this is the more explanations. And then we'll work on the second one. So now then we care about the energy per mode. So we have a lot of vibrating modes. This one. And we have so many vibrating modes. So what are the energies carried by each vibrating mode? I think it's at the back. 有没有多的白纸?
Yeah, I want to write the graphing thing.
Oh. I don't have white paper with me right now, but I'm sure there are some white paper at that. Yeah. And now we can think about energies. And energy is something. Do you think that energy is countable? Is the energy like it's just a lot of things, and then you can take portions of it, whatever you want, or if the energy is divided into blocks and blocks and blocks, and whenever you take it, you can just take it in a unit of a block. 就是大家可以想，这边我用中文讲一下。那我们现在要来讲能量分配的问题了嘛？
你可以想象一下，能量在你的想象里面，它是一个什么东西？就是它是像水，或是像空气一样，你随便拿一个袋子，你这样一捞，你捞多少就捞多少。还是说呢，它是一块一块的，像冰块一样，或者是像砖头一样，你每次一抓，你就只能抓一块。我们对于能量这种东西的想象到底是什么呢？那么 So, do I have explanation? Yes. Okay, then I explain it one by one. If you can think about how we treated energy in classical model, so here's a reminder for you. We already treated it when we were learning statistical physics, and here's a reminder for you. So we worked on the heat capacity of gas. And that was in the chapter from ideal gas to complex gases. And why is it complex? Because the particle is not a particle anymore. Now we are thinking about the particle, a pair of particles, and the particles can translate, they can rotate, and they can vibrate. And when we are distributing energies to all of them, it's like when we are heating up, we are pushing energies in the form of heat into the systems, and now the heat is distributed to every kind of modes that sucks energy. And some of them is translating, and some of them is getting into the rotations, and some of them is getting into the vibrations. And when we were deriving the model for the complex gases, we simply assume each degree of freedom contributes a certain amount of energy, and a certain amount of energy is just equally distributed to the degree of freedom. Degree of freedom is like this: when you are rotating and you have 3 axes, you have 3 possibilities of rotations, so you have 3 degrees of freedom. And now we just distribute all the energy to the 3 possibilities equally. We just simply say that rotations on X, Y, Z have exactly the same energy. And for rotations and translation, it doesn't produce big problems. But for vibrations, and here are something that we have to think about it more and more carefully. But when we were working with gases and people doesn't know the structure of molecules, so they just simply, okay, in order to start with, and we have to start anyway, and then they just assume that okay, and then we just treated it as the way that we did. And we have different kinds of vibrations. No, maybe this is not good. Yeah, maybe we have different kinds of vibrations, but we simply jump into a conclusion that different kinds of vibrations just contains exactly the same amount of energy, and that is how people work with the heat capacity of gas, and it just is still work in that kind of level. But for black body radiation, which is a more kind of vibrations, they just comes out together, and then it doesn't work anymore. And this is what we have for black body radiation. So for the classical model, we just simply say that no matter how many modes I have, and no matter how it vibrates, I just distribute the energy equally to all the modes, and every mode just exactly have the same energy. And then how we show it with the schematic, with the graph. So this is the increasing frequency, but the energy doesn't depend on the frequency at all. So the energy is just the same for everyone. So this is the classical thinking. But actually, this is a little different. If you would like to have the spectrum, experimental spectrum of black body radiation, you are somehow forced to think about this possibility. 然后我们现在用一种有点奇怪的方法在思考哦，因为
黑体辐射它是实验的结果，就是铁一般的事实就在那里。那现在的理论学家他们必须要退一步，就是好，那我现在想一下，所以我的能量到底是怎么分配的？我可以得到实验的结果。对啊，可是理论学家必须要把头低下来，你好好思考一下自己的思考模式要如何改变。这就是他们改变的方法。And this is how they change their ways of thinking to match the experimental results. So they just say that, okay, let's think about it this way. What if the energy distributed in each kind of vibration mode is depending on the frequency of vibration? If the vibration has a higher frequency and it has higher energy. And that makes sense. Yeah, that makes sense. If you use the model of simple harmonic oscillations, and if you calculate it, and you know that yes, that makes sense. And that was the time that people think, if that makes sense, then we just try it. Then try and see what comes out. So here is kind of a hypothesis. And here is a very important thought. So now the energy distributed on each vibrating mode depends on the frequency. So it seems like the number of energy distributed on each vibration is in a package. It's not like this one. And here's just a maybe you can think about it this way. So it's like we have so many students in this room and we have a birthday cake here. And now we have a question. We have to distribute these birthday cake to everyone. And how do you distribute it? Maybe for the classical thinking, what we do is we just smash the cake and make it into porridges, and then everyone just take a bite of it. So that's the way that the classical thinking is working. And for the quantum mechanics, then we are taking a knife, we cut the cake into pieces and pieces, and some of them are bigger and some of them are smaller. And then maybe when I am distributing the cake and I am counting, oh, here are the big guys and here are the petite guys, and the big guys maybe want more and have bigger pieces of cake, and the little ones or girls in diet, they don't want to eat, or some of them they are with a weight contest and they don't want to gain weight anymore, they don't want it, like that. So this is the two ways of distributing energies. 然后这边给大家打一个比方，就是你现在分配能量的问题，就有一点像是说，我们现在大家可以想象，如果我们一间教室有这么多同学，然后我们现在在一个庆生会好了。然后庆生会的前面我们就放一个很大的生日蛋糕，那我们现在要来分蛋糕了，我们要怎么分？然后呢，对于古典物理的想法就是呢，我们把蛋糕压扁、搅烂，然后开始算，我们现在应该有40个人吧，然后呢，我们就一人拿一只汤匙，一人挖一口，这个就是古典物理的分法。然后呢，量子物理的分法就好像前面有一个老师，然后这个老师就开始东看西看。有人上次跟我讲说他在参加什么降 BMR 的比赛，然后他不想要吃太多，或是有人说我刚刚肚子好饿，我们刚刚打了篮球，我现在超饿，我想要吃很多。啊，有人个子比较大，吃比较多；有人个子比较小，可能就吃比较少。然后老师就开始估计说，好，我现在大块就要几块，然后小块就要几块，然后我就开始切。然后就有的大块，有的小块，喜欢大块的就拿大块，喜欢拿小块的就小块。所以这个就是量子力学里面分能量的时候他们的分法，就是那个分它是切一块一块的，有大有小，有大有小。然后呢，前面那个把蛋糕搅烂，一人一口。跟后面那个切蛋糕一块一块的概念，我会觉得这个就是在所谓的量子力学的量子 quantum， 它是一个还蛮重要的一个想法。好 So the way that if you smash the cake and if you distribute it to everyone and if you cut it into pieces, and I think that is a very important difference between the classical way of thinking and the quantum way of thinking. Okay, so this is done. Okay. And then let's get into the third part. The third part is about the probability per mode. So in the classical model for the gases, for the complex gases, the probability of every mode to happen is just equal. We don't have any preferences. So that is because when we were working on complex gases, we just think that all of these molecules and they are flying, they are bumping into each other, and everything is averaged and everything is smoothed out. So that is the way when we are working with classical particle model, which is based on Newton's laws. But for just at that time, from the people who work with statistics, who is Planck's friend, 叫什么名字去了？等我一下，叫什么名字去了？我怎么一下子讲忘记还有什么名字？叫波兹曼。好，波兹曼就是普朗克的朋友，波兹曼。然后呢？Boltzmann's researches, and Boltzmann is a statistical physicist, and he is doing research on every kind of possibility distributions. And possibility is just not equally distributed. In some of the cases, if you have some asymmetry, if you have some special conditions in your systems, and sometimes the possibility is not the same for everything, and the possibility depends on the temperature as well. So. The Boltzmann distribution is very important. This equation is called a Boltzmann distribution, and if you learn semiconductors, and if you learn superconductors, and then you have to work on Boltzmann distribution a lot. And I just leave the derivation for the future, and I directly tell you the answer. Boltzmann just discovered that in this way of distributing energies, that if some of them have bigger parts and some of them is smaller parts, and if you distribute your energy this way, now the possibility depends on the frequency as well. And if your frequency is smaller, the probability to get the energy is higher. If the frequency is higher, the probability to get the energy is lower. So you can think, this is maybe another kind of fair. 这可能是所谓的另外一种公平吧。So you can think about, if you have a big piece of cake, is it fair to give everyone a big cake? Or, no, how should I say it? It's just like if you're playing lottery, isn't it? So when you're playing a lottery, and you have the biggest prize, and the prize is getting smaller and smaller and smaller, but you have just a certain amount of money. And if you have a bigger prize on the top, and you should apply a smaller possibility to it. And here are many little prizes, and there are little chances to get money, then you can have more possibility, and that is the way you prevent yourself from bankrupt. And somehow physics is playing it so with such a humanity as well. 就是现在这个概念，它有一点像是你可以看一下我们的乐透抽奖的制度是怎么设计的。就我们抽奖的时候，通常都会有一个头奖、特奖、特奖一台车子，然后头奖什么50万，然后呢，那个奖就越来越小，越来越小嘛。然后呢，你的奖越大，能拿到的人就越少。然后呢，你的奖越小，能拿到的人就越多。这个是因为呢，主要的原因是因为我们今年用来发奖的预算就是这么多，它是不会无限增长的。 所以呢，为了要兼顾抽奖的乐趣，跟兼顾大家都要开开心心的回家，所以我们就会去设计出一个这样子的制度，就是大家都可以开心，但是呢，又不至于到主办单位破产。然后呢，很有趣的是，物理学在自然学界，在大自然里面，它竟然也在玩一样的策略呢。我不太确定是人后来想的，还是怎么样，但是就是呢，波兹曼在做研究的时候呢，他发现某一些统计模型，它就会呈现出这样子的行为。好，就是你会看到说，它的能量 package 如果越小的时候，然后呢，那颗 particle 或那颗 charge carrier 或那个 vibration mode， 它得到能量的几率就会越高。但是如果这个 vibration mode 它一次就要很多，那么它拿到的几率就会变小。好，所以呢，这个就是古典跟量子力学两边那个想法上面的差异，然后呢，还有一些修正。这里 ，so here are some notes on it. So you can just write it down on your exercise. 所以这里是我刚才叽里呱啦讲一大堆，然后这个是重点折录。有些对科学哲学或者是思维比较有兴趣的同学啊，或是对人工智慧有兴趣的同学，你在这里就可以注意了。就是呢，你的古典，你可以看到人他在他有一个，他等于是你看，你可以比较蓝色的部分跟绿色的部分，你会发现呢，这两种思考模式中间突然有个断裂，就是那是前面一种思考的方式，它有它的时空背景，它有它当时的局限，所以呢，那时候的人决定用这样子的方式去思考，然后对于他们当时触碰到的一些 case， 像气体，上面那种思考模式是足够好的，但是呢，等到气体是物质嘛，是一颗一颗 particle。然后等到你要处理光的时候，然后呢，上面那种思考模式就弄瘪啊，就紧绷了嘛。他就我搞不懂事情为什么会这样，一定是我的思考模式有一点问题，我来思考一下这个思考模式到底要怎么改进。然后呢，我们就开始把前面那个全部都丢掉，然后呢，后面的 quantum mechanics， 然后我们再想象另外一种可能性，然后或者是呢，透过一些别的想法，然后去建构出一个新的思考模式、新的思维。然后前面那种跟后面那种之间好像完全没有关联性。这种状况在科学的发展上面蛮常发生的，就是每一次巨大的改变，基本上都会呈现有点像这样子的模式。所以就是你如果对人类的思维有兴趣的话，就是前面一种思维是一种典型，后面那种思维是一种典型。
Yeah, and now we have three distributions, and I just let all the explanation out, and here we have three distributions, and then we should get the total spectrum. We should get the total spectrum. And here's some changes. Here is another important thing. So what happens if you make the temperature higher? So what happened? So the result just tells us that when the temperature is getting higher, the intensity gets higher, and the position of the peak is shifted to shorter wavelength. Yeah, and this is what changes when the temperature is getting higher. So it changes the energy per mode. So when your temperature is higher, you are putting more energies into the system, and for the classical model, it is equally distributed to every mode, and every mode get more energy. So this is what happens when the temperature is getting higher in the classical thinking. And when the temperature is getting higher in quantum mechanics, it changes the possibility per mode to get the energies. The energy per mode is fixed by the frequency. This is fixed, but the possibility changes. So when the temperature is getting higher, the higher frequency modes, the modes who have higher energies, and now they have more chances to have energy. So when the temperature is increasing, and the distribution here is shifted to the right-hand side. Okay, so here are the two differences. 好，所以对古典的思考模式而言，当你的温度升高，等于你在同一个系统里面你塞更多能量进去嘛。那这个时候所有的能量都是平均的，然后分配到每一个震荡模式下面。那所以大家得到能量都一样多，然后大家就一起发大财。好，然后。我不知道为什么我看到那个这种线，我就很想要喊发大财。好，然后如果是我怎么突然笑我就忘了我讲什么。那对于那个资本主义社会，哎呀，这样子就很残酷了。就是你的温度变高的时候。然后呢，得到一大包能量的几率会变高。好，那些拿到一点点都很可怜，是不是资本主义社会？其实那时候的德国人，他们看到自然界的行为跟人类一样，他们很害怕哦。那时候他们觉得非常害怕，对，因为那个时候也是好像马克思主义也正在崛起嘛，对吧？所以他们看到大自然的反应怎么跟人类一样，跟资本主义一样，他们吓死了。好，总之呢，就是波兹曼他推导出来说，当你的温度升高，整体的能量变多，然后就是比较高能量，然后它得到能量的几率就会变高。Okay. So what else? Finally we come to the result. So the intensity of radiation is the three spectrums. You just superimpose the three spectrums together. You just multiply them. So you just get the number of modes, multiply it with the energy per mode, and then multiply it with the probability per mode. So this is what we get if you put the three spectrums together, and then you just get it for the classical one and the quantum mechanical ones, and then you just superimpose them, and you have the two curves. And this is just what we see from the classical models. When the frequency is increasing, then the intensity of the light is getting higher and higher and higher. And there is no limitation, which is very, very strange, which doesn't make sense at all. But if you use the quantum mechanical thinking, and then you can have a distribution like this. So even if the yellow curve, this is the possibility, is very high for the low modes, but here are two other friends. So this is the number of energy, and this is the number of modes. They are very little, and that is the reason why you have a 0 here anyway. And for the higher frequency ones, and this is the crucial ones. So for the classical one, because the crucial one is the possibility. So you have equal possibility for all the modes. So here you don't have any factors to stop the growing trend. But for the quantum mechanical mode, because we just know that if you want a lot of energy and then you don't have that much possibility to get it, so even if here is a lot of energy and even if here is a lot of possible modes, and because your possibility is lower, and then you have a lower intensity. So everything is perfectly explained. 好，所以我们最后做的事情就是把三条线把它叠在一起，然后你在脑内做一下做一下乘除，就是这三条线是相乘哦，它们是相乘的关系，你把它乘在一起。好，然后最关键的点就是那个 possibility of a package of energy to be accepted， 就是最关键的是黄色的线，这条线，就黄色的线呢，我们刚才就有解释过说，如果你的 vibration mode frequency 很高，它一次就要很大一块蛋糕，那它拿到蛋糕的几率就会降低。那这个时候就是因为它的几率降低了，所以即使这样子的 vibration， 它有很多种形式，它有很多能量，但是因为它的几率比较低，所以呢，达到最后的时候，我们的 curve 终于可以顺利的降下来，然后它可以得到一个跟做实验是一模一样的趋势。And when all the parameters they are somehow perfectly matched, and we have a peak somewhere. Here the middle class people， 这里就是中产阶级，刚好就是可见光。然后这里今天教给大家的这一串方法哦，就是你在任何有很多参数，然后你要去推测你最后会看到什么状况的时候，非常好用。就是你可以把你的参数就画图，这样子一张一张画出来，然后你画一下，就是你的 trend 是 linear 呢，是 logarithmic 还是 parabolic 或 hyperbolic。然后呢，你把你的线画出来之后，然后你就把那些线全部相乘起来，你就会知道这些参数全部加在一起最有可能会得到结果的点在哪里。好，我会觉得其实很多时候就是我们对于那个线的走势，常常都会忽略它的重要性。像你可以看到这边有3种走势嘛。一个是直线，然后一个是波兹曼 distribution， 还有另外一个是抛物线，是几何形状决定的。你如果对这些线有一个很清楚的概念的话，你在做对导的时候就会很快，就是做 modeling 的时候就会很顺利。So here you can see 3 trends. So we have linear trend, we have parabolic trend, and we have a Boltzmann distribution. And if you're very familiar with all kinds of distributions, and it really helps you to do modeling, quick modeling, I mean. So before you really start with all the derivations and all the calculations, and you can just apply those trends,
and you can have an idea about how things go. So you don't get yourself trapped in equations and in numbers and in strange derivations, and you don't get yourself lost. And you can always have an idea about what you're working on. So I really find the concept of train and superpositions is very, very useful. 好 ，OK， 都 OK 吗？好，都跟上。今天试试看能不能把 photo 也去讲完。好 ，Here are the good references. If you don't feel like you're satisfied, and you can download these articles and read it. So here are comparisons of classical and quantum derivations. Here are derivation of energy density. And this is Planck's original derivations and what exactly happened when Planck is deriving everything. So if you're interested, then you can read it. So this is Max Planck, and he is Einstein, obviously. And actually, when he is deriving everything that we just showed graphically, and he was making up answers, he is taking every kind of distribution and try to manipulate them and try to reproduce the distribution of the intensity profile. And when he get the result, and he was really shocked and panicked because he is not able to explain the distribution of that one, the h nu distribution, and he is not able to explain the distribution of Boltzmann distribution. He is totally not able to because he's a classical people. And to him, it's like during his derivations, and somehow he find a perfect coincidence, and he has to find a reason for it. And that causes Max Planck a lot of panic. 就是Max Planck 他自己在推导那些数学公式的时候呢，其实他是凑答案凑出来的。所以你在看他的 paper 的时候，你会觉得很痛苦，因为他完全没有推导可言啊，就是他的推导就是第一步跳到下一步，瞬间就跑出来了。他没有办法告诉你原因是什么，因为他真的没有办法告诉你。他就是看着实验的结果，然后跟他的朋友讨论，然后呢，他们就凑，把答案凑出来，就像我们现在的学生在写考卷一样，就是你已经知道标准答案了，然后你想办法把答案凑出来。就我们在做研究的时候，其实也是一样的哦，所以就凑答案，并不是可耻的事情。有时候它是你可以，它也是一个发现新东西的途径啊。对，所以我觉得那时候布朗克他遇到的困境就是这样，就是他的答案是凑出来的。So he was really， 然后因为他这个人实在是太谦虚了，然后他看到那个 perfect coincidence， 他并没有觉得很开心，他反而觉得很痛苦，因为他觉得怎么会这样子呢？他有点被逼迫着，他必须要去接受他无法接受的事情。但是这个我觉得我们在做研究是常遇到 ，but this is a very common. I think everyone who work in the lab just get this kind of experience over and over again, because I always think that how the nature is behaving is much bigger and wider than how human can think. So if you stick with the results, if you stick with the honest method to do measurements and the honest derivation and honest statistics analysis, sometimes you get spectacular results, and it takes a very long time for you to explain what's going on. So it's a little bit like you're creating something that you don't understand at all. But I think it's very enjoyable. That is a very enjoyable experience in your life when you're doing inventions or when you're doing researches. 就像我们这些进入以研究作为一种职业的人，然后或者是你以后你可能当工程师，你是以发明作为一种职业的人，这种状况常常发生哦。而且你习惯以后，你就会觉得每次遇到你都会觉得很开心，你会觉得蛮幸福的。因为就是你会发现说，比方说我是做物理学研究，是研究自然科学的嘛，那 你常常都会觉得说那些自然界的东西，它行为的模式，跟他们事情为什么会变成这样，往往是超过你的思维很有限，你的眼界也很有限。然后呢，你以一个有限的思维，想要去诠释大自然的事情，已经不可能了，更不要想你想要去控制它了，它不会替你控制的啦，你只能顺从它。对，但是等到你在做一些创作的时候，你发现，哇靠，我怎么创造出一个我根本不了解的东西？我觉得其实那种感觉是蛮好的，因为你就会发现说，哇，我其实很渺小，我懂的事情不够多，然后我总是在一个想要把某些事情搞懂的过程里面。我觉得其实那是一个非常对我这种人来讲，我会觉得那是一个还蛮舒服的过程哦，所以我选择了科学家作为我的职业。那我很多时候在看一些科幻电影，或是在看一些文学作品的时候，就是看到有一些人，其实那也不是想象啊，因为很多科学家真的那样想，就或是工业学家他们就这样想，就会觉得说，你了解你就可以控制，你了解你就可以怎样，你就可以创造一个完美的什么什么东西。我觉得那样子的想法，与其说是可怕，不如说是无知吧。真的，就是那种想法，其实它是一个，你会一直遭遇到自我挫折啦。就是像弗朗克的故事，他已经是一个非常谦虚的人了，所以他并没有精神崩溃。那如果是一个非常自大的人，遇到这样的事情，不如崩溃了。好 ，OK， 所以 and here is Ludwig Boltzmann. So I am not sure. I think maybe the student in mechanical engineering will be more related to heat and gas theory and statistical physics, and for the student in electrical engineering, maybe when you are handling electronic noises, and then you will get into Boltzmann's theory. 那我想电机系的同学，你应该是到要处理电子杂讯的时候，你应该会遇到跟热物理相关、跟波茨曼的理论相关的东西。Okay, and when Einstein just read the paper from Planck about the black body radiation, and he was very happy, and he just said that, oh, the concept energy is equal to h frequency. This is just another evidence that the energy is quantized. So he was very happy, but Planck doesn't buy it. He just said, what is that? I don't understand, what is that? So that is a very interesting thing. But Planck helped Einstein a lot. So when Einstein was like a rising star, and Planck helped him a lot, we just summarize it. And here is like, this is a very famous story, that the black body radiation and the photoelectric effect, so we are getting into it now, are like the two deficits in physics in the 1900. 就是在1900年黑体辐射跟光电效应是当时的物理没有办法解释的两个实验。然后其他的部分呢，就是大家都觉得，都差不多啦，好像已经没有看到可以继续往前发展的方向了，除了这两个东西以外。And we just explained the black body radiation, and we are explaining photoelectric effect later. And just from these two little deficits, and when you jump into the little hole, when you dig into it, and when you are thinking about it more deeper and deeper and deeper, and somehow the holes are getting bigger and bigger and bigger, and finally we just get into the new physics, the quantum mechanics. And the quantum mechanics, I think the central idea of it
is that energy is distributed in packages, just as what I explained with the cake, that how the energy is distributed, and the quantum mechanics is distributing the energy, like cutting the cake into pieces, and then the pieces can be bigger, can be smaller, and it's distributed to every object in packages and pieces and pieces. Okay. This is Max Planck Institute. If you're interested to do PhDs or postdocs, I really recommend you to go. Okay. Okay, I think we can finish photoelectric effect today. 但是我们要走快点。我觉得我今天应该可以把光电效应讲完，但是呢，我们的动作要快一点。So this is photoelectric effect. 我看这样好了。So, if you're interested, you can watch this video by yourself. I just directly go into the explanations. Okay, so this is how it was discovered. But anyway, let's just go into the. Okay. So, photoelectric effect was first discovered when Hertz was doing the experiment with radiations. So when the experimental setup is like he is building a cavity with the oscillating charges, and when the charges is oscillating, and he just set up another antenna on the other side of his lab, and he tried to measure the currents running on the antenna and see if the energy from the cavity is transmitted through the air to the antenna. But when he was doing the experiment and his assistant finds something really strange, this assistant just finds that if light is shined on the antenna, then the current is getting bigger. And they find that really strange, and they are not able to explain it, and they find it very annoying. So photoelectric effect just shows its face as in the form of noises in the experiment. 然后先跟大家说，那个光电效应它之所以会被发现，是因为赫兹，我们很可惜就是没有时间讲他的事情。赫兹是做实验，然后证明了电磁波的人。然后他在做实验的时候，他们的做法就是，在一个含了电荷的腔体里面，然后他让那个电荷就是变多变少，所以它就是有一个 oscillation 嘛。然后呢，他在实验室的另外端，然后就放了天线，然后他们在电荷的共振腔在共振的时候，他去测量它的天线上面的电流是不是也会跟着一起变大变小。然后呢，他们就发现，会耶，所以就找到电磁波了嘛。但是呢，有一个杂讯，就是他的实验助理发现有一个杂讯，然后那个杂讯让他们觉得非常的困扰，就是只要有光，尤其是蓝色的光或者是紫外光，当然那时候他们不知道有紫外光这种东西，只要是蓝色的光有照到它的天线上面的时候，他们的讯号就会突然变大。然后以他们那时候做实验呢，他们是没有办法解释这个状况的，所以他们在做实验的时候，就是把实验室都弄暗，就是黑的，有想办法不要看到那个 noise。可是其实那个 noise 是一个很重要的事情。然后我不太确定是赫尔兹教他做实验的，还是这个助理他自己弄，还是有人教他弄的，我不太确定。但总之这位助理就是接手这个实验，然后他就继续去研究说光照下去之后电流为什么会变大这件事情。So the assistant just carried the experiment out. He just continued the research that if he put the light and let it shine on metal, and he is measuring the current and see how he can change the amount of current. So what other parameters that changes the amount of current. So that was his experiment about, and this is how he designed the experiment. So for the photoelectric effect, here are some hints.
when you're doing the experiment, and usually you have independent variable, that is the variable that you can change by yourself. That is something that you can control. And here are dependent variables, so they are the outcome. This is the result. And the independent variable, just after a lot of experiment and after a lot of trial and errors, and the system just find that if he changed the intensity of the light, he can change the intensity of the light, and he wants to see what's happened, and he can change the frequency of the light. So here are two parameters to change. We can change intensity, or we can change your frequency. And the dependent variable, so this is the outcome. You can see if you have electrons or not. So if you get it, or if you don't have it. So with or without electrons. And you can measure the kinetic energy of the photoelectrons. The electrons, they are just like jumping out of the surface of the metal, and when they are flying out of the metal and they are running, and you can measure the velocity, and once you get the velocity, you can measure the kinetic energy. So here are two parameters to observe. If you have electrons or you don't have it, if you have it, measure the kinetic energy of photoelectrons, and you can apply the conservation of energies, and then you can do some researches on it. So this is how the experiment of photoelectric effect was constructed. And here's the experimental setup. So we have a vacuum glass tube. So it's made of glass, and the air inside was taken out of it. So here and in the tube we have two electrodes. So one of them, this is the target. So this is the target metal, and here is another metal, and this is the electrode this is the collector. So here are the electrons flying out of the target, and here's the collector electrode that can take the electrons and then let the electrons out from the tube and get into the electronic circuits. And just you have the source of the light. So this is the incident light. You can change the frequency of it, and you can change the intensity of it. The frequency is changing, just like you're changing the color of the light, and the intensity is something that you can regulate. You can, I don't know how they regulated it, but they just changed it. And then this is the electronics that can measure the signals. You have a voltage meter, so you are measuring the voltages across the two electrodes. And here is a variable power supply, and you have a current meter to measure the amount of current, but the power supply is variable. You can change the voltages to push the electrons back. This is a little bit strange. So when your electrons are running out of it and it's running in a certain speed, and you can just apply a counter voltages to stop it. So this is sometimes called stopping power, and that is their method to measure the kinetic energy of the electrons, because the voltage supply just inject electrons into the circuit and pushes the photoelectrons back, and you can just have the voltages applied when the current just stopped, and the voltages multiplied by the number of electrons is just the energy to stop it, and then you can have the kinetic energy per electrons. Okay, so this is the design of the experiment, and this is what they get, which is really confusing. So here, the fact is okay, the first one is he changes the intensity of light. The light can be very bright or it can be very weak. And he just changed the intensity of the light and tried to measure the maximum kinetic energy of the electrons. And here's the strange thing. He just finds the maximum kinetic energy of the electrons is just the same.
it's not changed by the intensity of light at all. And this is a little bit strange because if you use the way of classical thinking, if you have a bright light, if you have intense light, you are putting a lot of energies into your target, isn't it? And if you think it in a very instinctive way, I put more energies into my target, the photoelectrons get more energy. I would suppose they should run faster. I would suppose the kinetic energy of it should be higher. But that is not happening in the experiment at all. 所以大家可以看一下这个它的问题哈。实验很简单，但是结果的诠释很复杂。就是很多时候我自己每次在准备讲光电效应的时候，我自己会卡住。好，所以我们现在先来做第一件事情，你的光的颜色固定，然后呢，你把它从弱调到强，然后你的光从弱调到强的时候呢，你同时去测量我的光电子的动能。好，那如果我们是用一个很古典的方法去想这件事情的时候，我的光很强，表示我塞了很多能量到我的靶里面。我塞了很多能量进去，那这些喷出来的光电子应该要得到很多能量。得到很多能量的光电子应该要跑得比较快，所以这个就是古典的想法，就是你的能量塞进去，它就是很平均的全部distribute到每一个光电子上面，然后所有的光电子都跑得越来越快。所以这个就是一般的，这是古典的想法。可是这位做实验的人，不管重复几次，他都发现电子的行为跟他想的完全不一样。就是呢，即使你去改变光源的强度，然后呢，他就用那 stopping power 的方法去测量光电子的动能吧。结果那个动能完全没有改变，他就苦恼了，这下子怎么办？怎么会发生这种事情？ And here's a big contradiction between the theory and the experimental result. In such a simple experiment, that you are not able to get the result which agrees with the theory, and that was a really big problem at that time. 所以你看，你设计一个这么简单的实验，结果你的结果跟理论完全没有办法符合，这是个大问题。就是你那时候的人的思考模式，这是一个巨大的问题。好，然后呢，这是第一件事情。And then he just tried to, okay, the intensity of the light doesn't work. Then he started to change the frequency of the light. And then he just run through the spectrum. He just started from red to orange and yellow and blue and UV, the ultraviolet. And I think he was kind of lucky because he just chose the metal which he can handle, and then he just find that if the light is visible, if the wavelength of the light is in the visible range, we don't have any electrons, we don't have any current. But if he moves from blue light to violet light, and if you get a little bit further, more than violet light, and that was the ultraviolet light, and he started to detect the current, and yes, we get the electrons. And then he started to have an idea that maybe the crucial factor is not the intensity of the light, but it's the wavelength of the light. And for classical theory, this is totally speechless. And why is it like having a threshold for the electrons to getting out of the surface? And why is it depending on the wavelength of the light? Okay, so that was a very strange thing too. And then scientists stuck there for a really long time. 好，所以呢，再来呢，这位助理他就开始去改变光的波长。然后呢，他刚好应该也是幸运啦，就是他那时候选择的那种金属刚好就是在可见光，然后到 UV 波段有反应的那种。然后呢，他就发现说，当他去把光的波长越调越高，越调越短，就是频率越调越高，从蓝色到紫色到
到紫外线这段的时候呢，本来是没有电流的，突然之间就有电流了，所以它就是有一个好像有一条界限，然后只要你的光的波长超过了那个界限，一开始就会有电流，然后那个电流里面跑来跑去的电子，它的动能并不会因为光的强度而受到任何影响。那这个对于古典的理论来讲，这完全没法解释，就无言啊。对，怎么办呢？事情怎么会变成这样 ？So that was a lot of experiment results and a lot of searching around for the active parameters, and finally, Einstein collected all the results and tried to summarize it. 然后，我有把爱因斯坦的原点，我有把它放在牛医生上面。你有兴趣的话，你可以下载来看。我本来是想要把它放在期末考让你写报告的，但是我发现里面完全没有做实验，这样不太好，所以你就是想看你自己看。I just put the original paper by Einstein in the New 3 website, and if you're interested, you can read it. He just wrote it in a very simple way, using very simple languages, and he is collecting a lot of experimental results and try to get a conclusion from it. And this is the conclusion by Einstein. So, the experimental results just show that intensity of light is not an active parameter. It's not the parameter that changes the photoelectric effect, but the frequency of light is crucial. And the frequency of light decided if we have electrons or not, and it decided the kinetic energy of the photoelectrons. So that was the light from the dirty situation. 所以其实对于光电效应那时候是百家争鸣。所有的结果跟所有的想法乱成一团，然后当然爱因斯坦发现的不只是这样啊，还有很多别的，但是这个应该是以我们现在的程度最能理解的东西。别的还有什么 entropy 啦，然后还有一些别的，它有一些别的佐证，然后有一些别的推导，但是这个是爱因斯坦发现最核心的部分。Okay, so this is theory derived by Einstein. He just said that the kinetic energy of the photoelectrons is just equal to the H frequency of light. So this is from the incident light, and this is the reason for the threshold. So it's like a threshold energy, which is called the working function, and the energy put in by the photon should be more than the working function to kick the electrons out. For us right now, it looks very, very straightforward, but for the people in the 1905, this is very radical. 就是以我们现代人的观点去看这条公式，我们觉得哇，怎么这么直观？就很直观，就没有什么奇怪的啊，就反正你的电子嘛卡在金属里面，然后你的能量要超过一个 threshold， 一个阀值，要超过它才会跳出来。就是对我们来讲，我们会觉得那个图像看起来非常的直观嘛。但是以1905年代的人这样的想法非常激进，所以呢，他们而且怎么会用一个这么简单的公式就讲完了呢？对啊，他就是爱因斯坦，他就是可以用这么简单的公式就可以把它讲完。好 ，so that was Einstein's summary. And 9 years later, this experiment was done by Millikan, and he is the one who discovered the quantized charge of electrons. And he is a very, very great experimentalist. And he did experiment, and finally he just created different frequency of light, and then he measures the electrons and measures the intensity and measures the kinetic energy, and then he just finally rounded everything up, and he just proved that Einstein's theory was right, and the generation and acceleration of photoelectrons is tightly associated to the frequency of the light, but not the intensity of the light. Okay.
这个实验又是米利坎做的。米利坎是近代物理学里面一个奇葩，就是近代物理学大部分都是思维上的改变或是理论上的改变，然后呢，他是唯一一个就是做了很多很有突破性的实验的人，像电荷的量子化，是他用有机实验发现的，然后再来是光电效应的最终版本，也是米利坎做实验然后确定下来的。总之是一个非常厉害的人。好，最后 Photoelectric Effect 在电子学里面现在已经用到烂了，已经是基本款了。So Photoelectric Effect is just a basic phenomenon that using everywhere. So every kind of detectors, like for example, automatic door, or here are some photo multipliers. If you are detecting the light, and then if you want to amplify your signals, and we are using the photoelectric effect a lot. So every kind of sensor, photons, and every kind of amplifiers, and they use photoelectric effect a lot. And it's used in the solar cell too. So it's the sunlight, and we are regulating the work functions of our material, and we would like to get more electrons from your active materials. And I don't think that we are using semiconductors anymore because the work function is still too high. And I think people are generally developing the organic materials like plastic or some other materials that make the work function lower. And okay, so that's it. 然后光电效应，它就是一个是任何需要侦测光的场合都会用到光电效应，还有另外一种是这个是我不晓得这个在目前的工业上面有没有常在用，但是在做那个对撞机实验的人，就我啦，还蛮常用这个东西。就是你在侦测一些带电粒子的时候，然后那个带电粒子它会先撞到一种叫 scintillator 的东西，然后那 scintillator 它会放出光，然后这个光然后又再去就是一个金属上面的光电效应，然后这里是一连串的电极，你家的电压越来越高，然后就让电子加速嘛。然后你撞到靶之后，它就会喷出更多光电子来，然后它就是你的信号就会放大，所以这个是比较老式的信号放大器。然后再来是这个是solar cell， 我一下忘了，太阳能电池。对，那太阳能电池一开始我好像没有看过金属做的太阳能电池，大部分是那个半导体做的太阳能电池。就是半导体它是可以去调整那个 work function， 然后你就可以用可见光的波段，你就可以产生很多光电子，但是效率还是不高，所以现在大部分的主流是在用那个有机材料，就是用一些塑胶类的材料，然后去调整它的 work function， 然后去做出那个太阳能电池。好，所以呢，大概是这样。那么，但是近代物理学里面，逐渐过渡到量子物理这个阶段，还有一个很重要的是康普顿效应。但是康普顿效应，我们在一般日常生活，尤其是电机遇到的几率应该很小。这个是做那个材料分析的人会遇到的，然后这个是做高能物理实验的人会遇到的。那么我就放着，就是期末考的部分有一个是康普顿效应的原点的论文哈，所以有兴趣的同学，你可以读那篇论文写报告。Okay, yeah. So we just stop here for today. 好，感谢大家，我们今天上课就先上到这里。